Over the next 4 webcasts, we're going to take a look at some of the most important reactions of monosaccharides, and we'll begin with the process of mutarotation, which is an inversion of configuration of the hydroxyl group at the anomeric position. So the alpha form can interconvert to the beta and vice versa. And the way that this can be tracked, it can be followed by the process of specific rotation. Specific rotation, you don't need to know the details, but if you were to take, it's a reflection, it's a characteristic property of a pure compound. So if you were to take pure alpha D-glucose, a solution of that would have a specific rotation of 112 degrees, but over time that would evolve to a value of 52.7. Similarly, if you were to take a pure solution of beta D-glucose, initially you'd measure a value of 18.7, but again over time that would evolve to the same exact value, 52.7. When two different solutions, two different pure substances converge to a same value of a physical characteristic, you probably are dealing with an equilibrium situation where there's going to be an equilibrium mixture that is a combination of two different chemical species, and that's exactly what's going on here. The two different chemical species are the alpha anomer and the beta anomer that can interconvert with one another through the open chain form. So for example, if you were to wonder where that 52.7 comes from, well, it's just an arithmetic average, 36% times 112, which is the value for the pure alpha form, plus at equilibrium we have 64% of the beta form, which has a value of 18.7. And so the arithmetic average of those numbers gives you 52.7%. And so starting from either pure alpha or pure beta, we end up with a value of 52.7 because the equilibrium mixture will be the same regardless of where we started from. We want to look at the mechanism in 3 dimensions. What's going on here basically is we've interconverted the anomeric hydroxyl group in the axial alpha position into the beta position, and it's going to involve this open chain form. So let's take a look at the details of the mechanism. Basically, we'll follow a process that can either involve the cleavage of the bond within the ring, that's going to be the endocyclic cleavage pathway, or it could involve cleavage of the hydroxyl group carbon-oxygen bond on the outside of the ring, and that'll be the exocyclic pathway. And we'll begin there, and the key word to write down in both cases is the intermediate that's known as the oxocarbenium ion intermediate. So let's take a look at what the oxocarbenium ion intermediate is. Basically, we're going to protonate the hydroxyl group at the anomeric position so we can set up a good leaving group. Then we're going to see the oxocarbenium ion by a lone pair-assisted beta elimination, and you end up with this structure, the intermediate that's shown here, this cation that has positive charge on oxygen, but also essentially some partial positive charge at the anomeric position, and that's known as the oxocarbenium ion intermediate. The oxocarbenium ion intermediate can then take and do a nucleophile addition to that polarized pi bond from the beta face, and in this case now we've inverted the configuration of the carbon-oxygen bond. A proton transfer gives us the beta anomer. Alternatively, we could have set this up in this mechanism up in a slightly different way. Had we protonated the oxygen in the ring, we would have ended up with an intermediate that looks like this. That intermediate would then go on and do a beta elimination, lone pair assisted, and now what we need to do is to change the face by doing a bond rotation about that bond and show the opposite face so that the hydroxyl group can add into that polarized pi bond on the opposite side from which the cleavage took place. Now the new carbon-oxygen bond is set up to be in the beta position, and so we've generated the beta anomer. Those are 2 different mechanisms by which the mutarotation process can take place.